Hi, everybody. Welcome again this week at Rod's Office Hours. This week we're going to talk again. This is Oil Industry Insights. It's meant to just explain a few concepts in the oil and gas industry. And tonight we're going to talk about artificial lift, in particular rod pumps, and sort of the reason why we need artificial lift, and specifically how they work and what are some good uses of them. So if you have any questions as we go along, just drop it in the chat and we'll try to address them as we can. And yeah, welcome again. So first of all, what do we mean by artificial lift? What are the different types of artificial lift? Well, artificial lift is basically, you can think of it as pumping oil to surface. And so there's a rod pump, which is like a pump jack and a rod pump, sort of the classic oil and gas example. Electric submersible pumps, sometimes called ESPs. Progressive cavity pumps, really good for pumping solids. Plunger lift, or plunger, and combined with gas lift as well. These are sort of in gas lift, you're putting gas into the well to lighten the fluid column to lift oil and gas to surface. A plunger, you're doing very similar thing, but it's using the tubing string and a plunger to lift the fluid up. So we're gonna talk about all of these. We won't get all of these tonight, but first, I just want to touch on something. Why do you need artificial lift? You see a lot of wells with pump jacks and this sort of stuff out there. What's going on? And so, really to start with that, we need to rewind the tape a little bit and talk about reservoir depletion or drive mechanisms. And so when a well is first drilled, when an oil well is first drilled, and this is showing a trap where oil or gas can be captured. You have oil, sometimes you have water underneath or gas above. And what you can get is as oil is produced out of the well, the water is a very strong aquifer, strong water drive, and that'll push the oil up into the well. Other times you can have a gas cap, and so as the oil is produced out, the gas expands and actually provides pressure support. And because if you think, and we've talked about some geology stuff in the past where, you know, this is sandstone or limestone, this is in the rock, and it's not a big balloon filled with gas or oil. But this is a good example, good time when you can actually think of it as like a balloon. If you take some fluid out, the size wants to go smaller. It's rock, so it's not going to go smaller. The pressure is going to go down. And so here, a water drive, a bottom water drive or edge water drive will keep the pressure up. Here, gas pressure expanding will keep some pressure in the system. Here in this scenario, you have a couple of producers here. And then as you are producing the reservoir pressure down, as you're producing the reservoir, pressure goes down and you get some gas coming out of solution, filling up some of the space. And that can drive some oil production, but you lose a lot of oil recovery that way. And then I guess one of the things that I've seen very commonly is oil, gas on top, and water on the bottom. And you're getting contributions of pressure support from both sides. You also have one of the good things about water in the reservoir is that it can provide pressure support. But the problem is eventually this water is going to reach the well and you're going to have a heavier fluid that you have to lift. Same as when gas reaches down to a well completion, you could have a lot of gas that you have to deal with at surface. So there's lots of different depletion mechanisms and drive mechanisms, but really what they're doing is as you are taking oil out, oil or gas out of the system, the pressure is dropping. And so a lot of times, so this is known as, so this would be the first is primary recovery, where you're just letting the natural pressure drive the oil out. Then you go to sort of secondary recovery. And so in this example, so this sort of cross section, you have oil, and here's your producing well, beam pumping unit. A rod pump can be called a beam pump, can be called a pump jack. There's a couple of different names on them, but you have your producer well, and then you have water injectors placed around that producer, and you're putting water in here, and you're maintaining pressure support and also driving the oil, pushing the oil towards this production well. And you can see here in this sort of cross section, water comes in and is being pushed over to the production well. Oil is being produced out here. Sometimes, most times, this is not a perfect flood front, not the perfect straight water flood. You'll get some fingering here going through because the rock quality is different as you're going in this section. So you could get this bottom section water out first. So then you go from 100% oil cut to maybe 80%. And as the water goes along here, your water cut will get higher and higher. So here we're actually injecting water from surface to kind of try and maintain pressure in the reservoir. So this is all really great. We can keep producing this, but then I guess the question is, when do you know when you need to put a well on artificial lift? So there is a time, and it's there's lots of rock properties and depends on the depth, and there's lots of ins and outs to it, but it is a fairly simple graphical solution. So basically it comes down to two curves. The inflow performance curve we have here on the left, and the vertical lift curve we have on the right. And so basically what these two curves are summarizing, the inflow performance is we have our production well drilled, we've cased it, it might be horizontal, it could be vertical, it could be we've perforated it, or we could have fracked it. There's lots of different things you can do to complete a well. Well, inflow performance is, as it sounds, it is how is the oil and gas flowing into the well? So it's all out on the reservoir rock, and it's starting to flow towards this hole that we've drilled. What's that performance look like? And so typically you can classify that by, if you plot the pressure on one axis and the flow rate on another axis. And so if you have zero flow, so the well is shut in, then you'll get a shut-in reservoir pressure. So this is pressure W, pressure while flowing. At zero production, this is your shut-in pressure. So you can think of it as, so if this is 5,000 psi or whatever pressure, that is what the pressure is in the reservoir. I'll call it P reservoir. As you start to open the well up and it starts to flow, as it starts to flow, the pressure starts to drop as oil is produced. If you're flowing at a flow rate, say 100 barrels a day, well, then you can come over here and say, okay, now the pressure at the reservoir is now down to here, and then a higher flow rate down to here. And if you were to open the well up entirely and there was absolutely no restrictions in that well bore, your reservoir pressure would go to zero and you would be flowing completely. Max rate could be 1,000 barrels a day, could be 10,000 barrels a day. This is the absolute open flow. And so This relatively simple curve, well, it's a straight line, so you can't get much simpler than that. This describes all of the different rock properties, damage that's caused to the well. All of that is all summarized in, and also very easy to test. If I know what my shut-in reservoir pressure is, and I open it up, and I see what the pressure drops, and I know what my flow rate, I measure my flow rate, then I know what this well is going to produce at, how productive the sand face, how productive the reservoir is at that well bore. That's the inflow performance curve. Then this other curve, there's a little bit of a sort of kind of a hockey stick kind of curve here. There's also pressure and flow rate. This is the vertical lift profile or vertical lift curve. And what that does is once the fluid flows into the well, one of the unique things about oil wells is typically they're very, very deep. So 1,000 meters, 2,000 meters, 3,000 meters or more. So hence getting oil from the bottom of the well up to surface vertically really depends on what type of pipe you've put in the well. If you put in very small diameter pipe, there's a lot of friction there. You can't produce very much. If you put in very big pipe, then you can get a lot more production rate through the pipe. So you have to match up the right size pipe and the right type of completion for the inflow performance relationship that you have. And then where these lines intersect, that will be your flow rate for a given pressure. And then you get a nice stable flow. And we'll go into these curves because they're very powerful in monitoring wells and improving well performance. We'll just dig into them just a little bit further. So again, this is the inflow performance relationship. I had shown it on the previous slide as a straight line, which your reservoir pressure and then your flowing pressures. So a very easy curve. But really, in actuality, there's a little of a bend over here when you get into high rates, and what actually happens is because in the oil there is gas in solution, and so the same as when you open a soft drink, you take the pressure off of the soft drink, you see the bubbles come out of solution. You've dropped the pressure. That gas the liquid can't hold that gas anymore because the pressure's dropped. The bubbles come out. And this is actually the bubble point pressure. So this is the pressure at which the first bubble of gas forms in a liquid. And so as you drop your flowing bottom hole pressure, at some point you'll drop it far enough that gas will come out of solution, and that interferes with the smooth flow of the fluid, of the liquid. So that's why you get this little bit of a bend here. But it's simple to think of it as just as a straight line. So, and that's our inflow performance into the well. Skin damage. So what does plotting this up tell us? So we have our initial conditions. Maybe when we first brought the well on, we did a step rate test. We floated at different rates, and we got a curve, a line. And you produced the well for a little while. If your reservoir pressure, again, like we talked about, starts to deplete, then what we're going to see happen is this is the reservoir pressure, the shut-in reservoir pressure. If this pressure drops, then you'll just get this line will just come parallel. Because nothing has changed in any of the rock properties. We're just starting at a lower pressure. So it's pretty easy for us to see as we take out so much volume, the pressure drops this much. that gives us a good idea of how much oil we can actually access, or gas, because it's a simple tank. Then take this much pressure, we take this much volume in, and the pressure drops this much, then we know we can only get down to a certain level. So we can then calculate how much volume we can take out. So, but in that case, it's just reservoir pressure dropping that's causing this line to come down on a parallel line. When the slope of this line changes, so the pressure hasn't dropped, but say we can 3 months later, we come and we do another production test, and we see, oh, now our pressure is much lower. At the same pressure, we're getting a much lower flow rate than we were before. Well, this can be indicative of formation damage, which is called positive skin. So in your flow calculation, what's happening is, for example, say we drilled a well and we perforated, and the well came on this track, and then over the course of time, some of the rock properties have changed. There could be fines or salts or things being mobilized in the formation that's starting to choke off that flow. Then that's when you see this change in slope, making being indicative of natural damage or induced damage. Something's changing, affecting the inflow of fluid into the wellbore that's independent of pressure. It's probably a damage, which then is a lot of times a good trigger to go and stimulate a well, either pump acid or even go in and bail out sand, that sort of thing. There's all kinds of things you can do to clean out and clean up a well to get rid of the damage so that you're back on a more productive track. So that's for the inflow. On the vertical lift, so now we're trying to get the fluid. So we've got our oil and gas into the bottom of the well. Now we need to get it out of the well. And this is, so really then you're talking about a change in pressure. There's 3 terms: potential energy, kinetic energy, and friction. And this term here is actually probably one of the terms to know in oil and gas. And that is pressure, potential energy, equals rho GH. And that's density times acceleration due to gravity times height. And because height is always a big number, usually, gravity is always a constant, but it's 9.81 meters per second in the metric. And then the density of the fluid. And something that we've seen before is gas is always on top of oil, is always on top of water because of the difference in density. And so you can have, gas is much less dense, but water is say 20% more dense than oil. Usually, again, depends on the oil type. But so when the fluid changes, if you're water flooding, if you've got a water pressure support, if you start to get water cut, this is going to change this hydrostatic pressure. So that's always a good formula to know, either in production or in well control. Then you have kinetic energy, which is just, again, density times the fluid viscosity. So that's the fluid flow in the pipe. And then friction loss, which again, as you flow faster, as your fluid velocity gets higher, there's actually more friction acting on that fluid. And so so this is your gas liquid ratio. Depending on how much gas is in the system, you can see different types of flow. Here's dispersed bubbles. Here's bubbly slug flow, where you get a big slug of gas. Then you'll get potentially churn. And then you'll get annular flow, where the gas is coming up the middle and the liquid is sticking to the sides, to the annulus. and then misflow, where it's really mixed together. So those also have an impact mostly on this friction term. You see this does make a difference at surface when this fluid comes to surface and you have to handle it in your oil separator. From an operational point of view, you want to have this slug flow is hard to deal with because it causes slugs coming into separators and equipment. You kind of want to keep, and so that's why you try and size your completion size so that it matches your inflow performance relationship. So, but from these three terms of getting liquid fluid from the bottom of the reservoir up your tubing, then you end up with a vertical lift profile. And so again, this is bottom hole flowing pressure and this is flow rate. Then you can see this curve has this kind of funny bend in it and then goes off this way. And so what's happening here is at lower flow rates, gravity is more dominant. And so as you start to increase your flow, you'll get a bit more change in density. And so that's where you see this pressure sort of go down first, because the density is you're actually getting lighter. Just see if I think there's a question here. What causes pressure drop in vertical lift? Oh yeah. What causes the pressure drop? Yeah. So what's happening is if you're flowing slow, the liquid is pretty dense. But as you get it, you can get it flowing, as you start flowing here, then the bubbles start to form and you start to lighten the fluid column. So then you get this pressure drop. And then once you get to a certain flow rate, then friction takes over. And so then basically the harder you flow, the more friction you get as you're flowing. That's what causes the pressure to go up. So here the lightening of the fluid is actually helping you, and here friction is starting to hold you back. So that's a bunch of some simplification. It's not simplifications. It's what's going on physically, but this is very easy charts to generate with minimal well data. You don't need to have a lot of rock properties. You don't actually even have to know what tubing size is in the well. You can figure it out from your pressure readings. So why is it important? Well, and why does it apply to artificial lift? Well, as long as these two curves intersect, my inflow performance curve and my vertical lift curve, as long as there's an intersection point here, I'm going to have a flow rate for a certain pressure. If they don't intersect, so if my inflow performance curve and my vertical lift curve, if there's no crossing point, then there's no solution where I can get a flow rate no matter how much I drop the pressure. I'm dropping the pressure but the well get inflow into the well, but I don't have enough pressure left over to lift the fluid out of the well. So this is where you get no flow, or what we call a dead well. So a lot of wells, when they initially flow, they'll flow naturally, natural flow early in a reservoir's life. But then in this example, one way it could happen is the reservoir pressure drops far enough that then you get a dead well. Another thing that could happen is you could have skin damage happen so much that it actually gives you a dead well, or you could have something strange happen in your tubing that actually it causes it to move up. And for example, if you have scale or choking behavior or damage in the tubing, you don't have enough pressure then to lift on your vertical lift profile or lift on your vertical lift curve. So in this dead well example, we use artificial lift to change the vertical lift profile, or a bigger size tubing. Sometimes if you upsize the tubing, you'll actually cause this intersection again. So that's how you go from natural flow to needing artificial lift. So, and again, then you have lots of options to pick from, and some are better suited to different situations. We're gonna just talk about focus on rod pumps now, but these other ones we can deal with later. And so in rod pumps you'll see almost exclusively onshore. You won't see them offshore that much, and there's some good reasons for that. And I think once we just walk through these rod pumps, it'll become evident when we talk about gas lift. So what's a rod pump? Well, this whole system is, you could refer to as a rod pump. So you may see these at surface, driving around Alberta or Texas, on land, or for sure you've seen them on TV. There's a pump jack or pumping unit. This is the surface equipment. So this is what puts the energy into the system. That gives us a bit more, overcomes that potential energy. And then it's connected through the wellhead, Christmas tree, down. So there's a rod string. We have sucker rods, they're called, down to the downhole pump down here. And this downhole, and this is run inside the tubing string. So you have, as we talked about previously, you have your casing cemented in with an annulus, and then your tubing run, and then inside the tubing would be a sucker rod. And that sucker rod would run down, and on the bottom of the sucker rod, there is a pump. And this pump is probably one of the more simplest pumps you're going to find. It's originally, I think, from the Roman times is when they did this. It's also the same sort of pump you see for pumping water, like in a old-fashioned prairie kitchen sort of thing. And all of this is, it is basically two balls, they call it a traveling valve and a standing valve. And these two valves, so as this pump jack goes up and down, this pump plunger goes up and down, and the traveling valve travels, it moves, and the standing valve stays in place. So how's that? What does that do for us? Well, here is another representation. So what you see is you start off with the traveling valve high at the top of the stroke, over here, point A. Then you move down, this moves down in point B, and then you're in fluid. And you can see here, the traveling valve is off its seat. So the seat is sort of the round thing that the ball sits on. As it's moving down, it's floating. And the standing valve is staying in place. Then when it's down at the bottom of its stroke, it starts to come back up the other way. And so it picks up the load of the fluid. And then the traveling valve seats, and then the standing valve is now floating. So this is probably a good way to see it. It's just just from a trade show a few years ago. So, and this is a model mock-up of, so you can see down here, here's the standing valve. And it's just a little ball, metal ball. And here's the traveling valve here. And so they just got a little model of a supposed pump jack. But he'll stroke this. And so you can see, here's the traveling valve. It comes up, it's on its seat. And now as it goes down, see, it floats. And the liquid goes past it. And it comes up, it's seated. It's going to lift all that liquid up. It goes down. And then here's the standing valve. as it's coming down, that standing valve, it seals off on the downstroke to keep that fluid in place. So, and that cycle just continues. It's just those two balls. Again, when you see that pump jack going, the donkey's head going up in the air, it's on the upstroke. And that traveling valve is sitting on its seat and it's lifting the oil out of the well. Then when it goes on its downstroke, now the standing valve is in position. It sits on its seat and the traveling valve floats down and then picks that fluid back up. And then just stroke by stroke, that's what pumps the oil out of the well. And you're doing this because there's not enough energy in the reservoir to drive the oil out. Or oil and water at this point. This is oil in this demonstration, but you can have also water in here as well, or a combination of both. That's how, and that's why you see so many pump jacks on so many wells. This is helping getting the oil out of the reservoir. And so a well that would be dead, would not flow, you can install a pump in there and then make it a very productive well. Again, a really, really good real world model. Again, standing valve, traveling valve. One of the things that let me start this video. Oops. Let's go back. So here you see it, and this is in cartoon form. One of the things that you can do on a pump jack is you can put a load cell on those sucker rods that are going up and down, and you can actually measure the load that's happening. And so here you see there's some gas interference. So what you want to see is on the upstroke, that load comes up nice and smooth, and then on the downstroke, you should see the load come off of the traveling valve. When there's a lot of gas interference, that can get in the way. Here's fluid pound. There's so much gas going in here that it's actually filling up. So you see the standing valves coming off. So now the gas is coming in, and gas is compressible. So now the pump jack is, say, halfway down its stroke, and then the ball hits the liquid, and that is what they call fluid pound, and that can cause you to damage the pump and have to have the pump changed out. This is tagging. There's another one, yeah. And so a pump off controller is a piece of technology installed on pump jacks so that as you are pumping fluid here, you see you want to have a nice square pump card, but as you start getting, your pump is too big for your inflow. So what's happening is you're starting to get gas that's in the annulus come in, as well as the oil that's coming in, because the pump is too big. So what a pump off controller will do is it'll see when this gets too much, and it'll shut the pump jack down and allow the reservoir fluid to come in, allows the inflow to catch up to what's being pumped out. And so that way you get a more efficient pumping system, and you don't damage these balls and seats, because they're really just little metal marbles that are on smooth round seats. And then there's some, you can determine other things that are going on in the well by different sorts of pump cards. So super useful. We go back to our demonstration model. Now he's going to simulate getting gas into the pump, and so he does that by pumping very hard. But really, what he's trying to simulate is if you had gas coming into your pump barrel, you see that you get a lot of gas coming in, and then now this traveling valve is going to have to get through that gas and then hits the liquid at a very much more higher speed than normal. So that can cause a lot of wear on the pump parts. So, and you can also see the standing valves also chattering and moving around a lot. Again, in artificial lift, you want to keep the moving parts moving smoothly and not having shock or changes from gas to liquid. So that's always good to keep it slow and controlled, but sometimes you don't know that until you get a failure or you collect more data. So, but again, very simple pumping system. It's just 2 check valves is all that you're using. That's what all of these pump jacks are actually. That's how they're getting oil out of the ground. And this is a service rig, and what these guys are doing is they are pulling sucker rods. So you see these things in the drilling derrick. They're actually sucker rods. Those are the metal rods that are screwed together that connect the pump jack to the rod pump in the well. And so there could be hundreds of these in a well, and because you don't have one long string of steel holding all these things together, it's one sucker rod at a time. And they call it, so you can see how they're pretty long, but still there's a lot of them. And so there's a lot. So when you have to do a pump change out, you get a service rig in, and you'll tripping sucker rods. So you have your tubing, and then inside your tubing, you would have sucker rods. At the bottom of these sucker rods would be a rod pump, and put a new pump on, and then run the sucker rods back in. There, just on the side there, you could see the pump jack, that horse's head of the pump jack, that's taken off, so the drilling rig or service rig can get in position to pull the bottom hole pump. So yeah, that's the connection from pump jack down to the rod pump. Oh yeah, this one also. So now this is the pump jack. So you can see back here you have an engine that's powering the pump jack. This is a gearbox, this section here. And you see the pump jack is, and this is the horse's head. And see, here's the sucker rods going down in the well over here. So one of the great things about pump jacks is they can be very efficient. What these guys are doing is they're adjusting the weights. So you can see these big pieces of clumps of metal here are pump jack weights, and they are positioned so that they balance the weight of the sucker rod and the liquid that it's pumping up. So, because what you want to have is that. I think they'll move them a little bit closer to they move them a little bit closer in, so that the weight, those weights equal the weight of the sucker rods. Then it's very efficient for the motor to drive this unit around, because as it's pulling the sucker rods up, the weights are actually falling over, and so it kind of, when it's in balance, it doesn't take very much energy at all to use a pump jack to pump oil out of the ground, which is one of the reasons why they've been so popular, is because you're putting your own sort of flywheel into your pump. So so that's why they probably won't go out of style. There is some alternatives to rod pumps, some hydraulic pumps, and some other things that you use. But again, because of the the energy efficiency that you get in a pump jack. That's one of the reasons why they're so popular. So, so now we have the reservoir conditions to set from natural flow to artificial lift. Rod pumps, very efficient and a very simple system. But one of the limitations is the amount of fluid that you can pump is really dependent on the size of the pump and the stroke of the pump. And so, there's some pretty big pump jacks out there, but eventually they get so big that it's unmanageable. So electric submersible pumps are a really good option if you're looking to pump a lot of fluid. So we can just touch on that here briefly. So yeah, here's electric submersible pump running a well. It has a motor and a centrifugal pump. That's, again, it's electric and it's submersible. So, and it's pumped. So you use electric power and you run it into the well. And then your pump is at the bottom of the well. That's a little bit different setup. But then at surface, you really don't see very much at all. So those are some of the advantages. Some of the complexities is that all of your connections, your electrical connections, and how the pump goes together, all has to withstand reservoir pressure, well pressure. So, but at surface, instead of seeing a pump jack going up and down, really you'll just see kind of a very small. Here's your wellhead. You'll see a pumping tee, and then the telltale sign is an electrical cable, an electrical feed through going into the wellhead. And typically they're for more higher volume applications, or where your space is limited, or offshore where you need some additional safety features. And I think, yeah, so here's just an animation of an electric submersible pump. You see fluid coming in from the reservoir. Then you have a motor, and this fluid goes outside the motor, the electric motor, and goes up past. Here's the electric cable, and again, this has got to be sealed so that you don't get any reservoir fluids in there. And then between the electric motor and the pump, there's also a number of seal sections to keep reservoir fluids out of the motor. That's very critical. You want to keep the motor cool, but you don't want to get oil and gas inside the motor. But this is electric submersible pumps. We'll pick that up another evening. I think rod pumps is very interesting. This is just another alternative that you can do on an artificial lift. And we'll go through some other types as well later. So that was office hours for this week. If you're watching on YouTube, you scan this QR code to sign up to view more office hours as they come out. And then also you can check out our site. Okay, thanks everybody, and see you next time.